Hello, my name is John Levin. In this series, I'd like to share my experiences designing and building a prototype Snowflake task queuing system for updating Snowflake tables from SQL Server. I first started working with relational databases more than 25 years ago and have designed and built two enterprise-scale data mart systems using Microsoft SQL Server technologies. In the past few years, I've worked with Amazon Web Services and most recently Microsoft Azure. Several months ago, I was asked to explore potential solutions for publishing content maintained in a SQL Server database running on an Azure virtual machine to a Snowflake warehouse. Having little knowledge of Snowflake functionality and no hands-on experience working with Snowflake, this project has been a fascinating, enjoyable, and occasionally frustrating voyage of discovery. This presentation assumes little or no prior Snowflake knowledge. Snowflake provides a rich set of tools for working with data. I've come up with one solution. I'm sure there are others. But while building this, I've learned a lot about Snowflake, and I'd like to share some of that knowledge with you. This will be a deep dive. I've broken up the videos into intro, code walkthrough, and demo sections so that you can skip between areas of interest. But because of the total length, you should be aware that if I cover a concept in a segment, I will probably not repeat that information in a later segment. This system is still being developed, and the scripts and procedures are undergoing refinement, but the system works and has met the objectives. The source SQL Server system is running on Microsoft Azure, but other than the two integration objects used in the Snowpipe processing, the source could just as well be within Amazon Web Services. This presentation will be exclusively focused on Snowflake processing. In the future, I hope to present a demonstration of the SQL Server source processing used to create the data files used as input to Snowflake. So why publish SQL Server to Snowflake? I'm assuming you've come to this video with some awareness of Snowflake's unique potential, but here are a few things that excite me about Snowflake, all but one of which have been leveraged in the system you're about to see. First and foremost, Snowflake was created to be a pure cloud data warehouse. Its three-layer architecture separates storage, computation, and cloud services. This is unique and provides the potential for nearly unlimited scalability and cost management. Snowflake's design is also cloud vendor agnostic and can be used and potentially shared across multiple cloud vendor environments. Zero-copy clones can be programmatically created for specific or all Snowflake objects within a database, with no additional costs for unmodified snapshots. Snowflake's time travel takes full advantage of cloud architecture by providing real-time historical access to its database objects based on their state at a specific date and time, or even before or after a specific DML update statement. Database objects which have been dropped can be subsequently undropped via time travel. Now that's pretty cool. Failsafe provides additional emergency recovery access to historical data which cannot be accessed via standard time travel queries. Change data in Snowflake tables can be automatically captured to Snowflake streams, which can be subsequently queried to propagate Snowflake table inserts, updates, and deletes to other Snowflake tables. Streams can also be triggers to initiate Snowflake processing tasks. Snowflake pipes can be created to continuously load data files as they are created in cloud staging areas. Snowflake tasks are scheduled to run commands or call stored procedures. They can be triggered as data is inserted into a stream object based on table updates and can also be constructed into task trees with parent-child dependencies. Snowflake has been designed from the ground up for data sharing, which means once data is inside Snowflake, it can be safely shared across organizations and cloud vendor environments. Snowflake sharing and the data exchange is not going to be discussed in this presentation, but I hope to have a future demonstration of this important feature. Finally, during this process, I've come to appreciate Snowflake's excellent documentation and moderated community forum, where members post questions and receive useful answers. There's also a significant amount of Snowflake how-to content on the web. I'm hoping to do my bit by contributing to this. Before we continue, I'd like to say a little bit about interacting with Snowflake. Snowflake has a web-based console. After you log in, you see a screen like this. You can create worksheets to build and execute queries, and you can get some basic system information. When you're in Snowflake, you have to create a context to execute your queries and to be able to see system information. In this case, I currently am connected to a role sysadmin, and I am connected to an extra small-sized warehouse, which we'll be using for this demonstration, a database, and within that database, a schema. I'm currently logged in as the sysadmin role. Because of my profile, I can change this to other roles. You can see we have account admin, which is the highest level role, security admin, and task admin, which is a role I have created, and then a user admin. If I go to the account admin role, you'll see that we have additional options at the top of the page. I can go to account and I can get usage and billing information over time. In addition to the worksheets, another thing that I can do is go back in the history of the queries that I've run and get detailed information about the queries and results. Snowflake has an alternative console that's in preview mode. You can get to it by clicking the Preview App button. When you do, you'll log into the preview version of the console. It looks like this. It's a different interface. You may prefer it. It has a little bit more information about the objects inside the database and the schema. In this case, all of my objects are in the work schema inside the JLo database. And you can see, I can see all of the major object types and drill in and get information about those objects and actually be able to see what's inside them. In addition to the Snowflake consoles, I can also use third-party query tools to connect to my Snowflake database. In this case, I'm using dBeaver. I don't have all of the functionality available in the Snowflake console. For instance, the ability to look at query history isn't here, but there's nothing to prevent me from having a console window open in addition, going back and forth between the two. As with the Snowflake consoles, if I don't want to fully qualify all of my database references, I can create a context from my query windows. In this case, my connection has set my database context, and I can select my schema context here. I can also do this manually. First, all of my available schemas, and then to select one of them. Now that I have this context, I can see the tables that are inside the schema. As with the console, dBeaver has an object explorer, and I can drill into the schemas in my database and look at the individual objects inside. Let's review the system design. There's going to be a lot of content here, so don't be too concerned if it's difficult to follow. I'm going to be going through all of the Snowflake objects and programming in gory detail, as well as running demonstrations of the processing, but I think you'll do better having a run-through of the entire system before we dive into that. Our objective is to propagate table changes from a SQL Server database to a Snowflake database. The table structures need not be identical in the two environments, but our update logic needs to ensure that changes in the source system tables are properly applied to the target, so that the post-update Snowflake tables represent the state of the source system tables. The source SQL Server system, in this case, has an ongoing data ingestion process called aggregation. Periodically, aggregation is paused and an update cycle called distribution is commenced, which updates a group of reporting tables. The source system distribution cycle is driven by a data structure which contains update key groups and a value which identifies change data in those key groups. A new process will be added to the source system distribution cycle, which will create data files based on the changed data, which will become input to the Snowflake update cycle. The internal processing of the SQL Server source system will not be discussed in this presentation, but a future demonstration will be created on that topic. In the processing flow, changed data files will be consumed by Snowflake as soon as they're created in the source cloud staging area. These files will be continuously loaded into a semi-structured Snowflake staging table. Once Snowflake starts staging the update files for a target table, referred to as an entity, it will start looking for a time when there are no remaining files to be staged for the entity. At this point, it will begin its update cycle to apply the staged update data to the target tables. In some cases, updates will be able to be processed concurrently. This includes updates for different effective dates. In other cases, the updates need to happen in sequence. This includes deletes, inserts, and updates for the same effective date, where deletes will be processed before inserts and inserts before updates. Within deletes, inserts, and updates, the sort order of the input file name determines the order of processing. The convention is to include a date and time in the file name to allow files to be processed oldest to most current. For groups of updates which can occur as parallel jobs, a separate task will be enqueued to handle groups of updates. The system will dynamically create these tasks as needed to process update jobs. The system will understand the parent-child relationships of update jobs, which must be run in sequence, and a corresponding task will not be created until the parent job is completed. A maximum number of concurrent tasks can also be defined to prevent overloading the warehouse. 3 tasks will orchestrate all processing. First, a start task, which when it executes calls procedure SP entity start as its handler. SP entity start first pauses the ingestion pipe after all files have been loaded to the Snowflake staging table. If the pipe cannot currently be paused because files are loading or waiting to be loaded, it exits and waits until the next start task execution to try again. Once the pipe is paused, the job list table, which defines the individual update jobs which need to run based on the contents of the update staging table, is populated. Subprocedure SP set job list dependency is next called, which updates the job list table with the parent job ID of any job which has a precedence prerequisite, such as an insert job processing the same version date as another delete job. Next, the task list table is loaded with one entry for each distinct version date in the job list table. These will become Snowflake tasks, which can be run in parallel. Note that a maximum number of parallel tasks for each entity can be set in the app config table to prevent overloading Snowflake warehouse compute resources. The last thing that the SP entity start does is to dynamically create and activate a process task. When the process task executes, it calls procedure SP entity process as its handler. SP entity process first calls SP get next job to get the job ID of the next to-do status entry in the job list table, which is ready to be run. If there are no to-do status jobs which can currently be run due to parent job dependencies, it exits and waits for the next execution of the process task. If a job can be run, the procedure calls SP start job task, which determines the next task ID in the task list table with a ready status. If there are no available tasks, it exits and waits for the next execution of the process task. If there is an available task, it gets marked as busy, and a Snowflake task is dynamically created and activated, which contains the task ID. When task ID task executes, its handler is SP entity task, with the task ID as its input parameter. SP entity task retrieves the job ID from the task list table and then all of the job specifics from the job table. It then calls the appropriate delete, insert, or update subprocedure to apply the updates to the target Snowflake table. When all jobs have completed, SP entity process dynamically creates task TA entity end, whose handler is SP entity end. SP entity end creates a cloned copy of the target table, clears out the stage update table in preparation for resumption of file ingestion, and finally resumes the suspended ingestion pipe. Here's a simulation of multiple entities being processed simultaneously. As previously shown, source system data is piped into Snowflake update staging tables. Multiple parallel tasks are spawned, observing update sequence rules. After all update jobs complete for an entity, the target table is cloned. This is the beginning of the update process. Files have been created in AWS or Google Cloud Bucket, or in our case, Microsoft Azure Blob storage. As shown in this diagram, a number of Snowflake objects have been created to process these files. Note that the names used in this application are listed in parentheses underneath each object. In a few minutes, we'll be looking at the scripts used to create each of these objects, but let's first define what they are and what they're used for. The PI map update pipe object sits between external cloud storage and internal Snowflake storage. The pipe executes a Snowflake copy into command to load external files into a Snowflake table. It directly or indirectly references 4 Snowflake objects. The NI Hub JLO notification integration object provides an interface between the Snowflake pipe object and the cloud message queuing system. Through this interface, the pipe is notified when new files have been added to a cloud storage area. The SI Hub JLO storage integration object stores an identity and access management, or IAM, entity for external cloud storage, along with an optional set of allowed or blocked storage locations. The ST map update stage object references the storage integration object. It is a named external stage referencing a specific cloud storage area which will be processed by the Snowflake pipe. Once the stage object is created, the associated cloud storage area can be referenced via the stage object name preceded by an @ sign. In this case, @st mapUpdate. The FF-hub JLO CSV pipe no header file format object defines the options in use for the pipe copy into command. Note that the file format can be referenced at the stage object as well to be used by all copy commands for a stage location. The SM mapUpdate stream object has been created referencing the TB mapUpdate table loaded by the Snowflake pipe. When the pipe inserts rows into TB mapUpdate, the stream SM mapUpdate will automatically track changes to the table. A task object is a scheduled execution of a SQL statement, which can include a stored procedure call. It also references a Snowflake warehouse where the task computation will take place. Although this system doesn't use the feature, tasks can be arranged in trees, where a root task can have child tasks which are linked through predefined dependencies. In our system, when pipe PI mapUpdate begins loading files for an entity named mapUpdate into table TB mapUpdate, stream SM mapUpdate will capture those table changes. Task TA mapUpdate start is waiting for changes to stream SM mapUpdate and will execute when the stream is changed. Task TA mapUpdate start calls stored procedure SP mapUpdate start, which begins our update processing. But before we continue that, let's take a look at some code. Finally. I've written a number of scripts to create the various Snowflake objects used in the system. Let's take a few minutes to look at them. For this Snowflake account, I am able to set my context to the account admin role, which allows me to create the John Levin account and grant the account admin and sysadmin roles to it. Next, I created a warehouse for my compute tasks to run in. Because this system is for proof of concept and I'm trying to conserve costs, I created this warehouse with an extra small size. This will accrue the smallest number of charges per compute credit, but I can easily change this warehouse to a larger size in the future if needed. Next, I created a database to house my schemas. I've created two schemas for my database objects. First is the work schema, which will have all of my persistent objects. It includes tables, streams, views, stored procedures, and the entity start task. I also created a separate queue schema, where the dynamically created task ID tasks running the table updates will execute. I did this because there could potentially be thousands of these tasks running concurrently in a production system, and I wanted to separate them from the control tasks for monitoring purposes. As you saw in the last section, I need a storage integration object to provide IAM credentials for the stage object used by the pipe, which will point to the cloud storage where my input data files reside. I also need a notification integration object, which the pipe will reference for notification when new data files have arrived for processing. The stage object points to a specific cloud storage folder where the mapUpdate input files will be piped from. Once created, it can be referenced by name, prefixed with an @ symbol. This is the file format used by the mapUpdate pipe. I've specified some of the file parsing options for the pipe's copy into command to use when processing the input data files. In this case, the files will be plain text with pipe delimiters. There will not be column headers, and leading and trailing spaces will be trimmed and blank lines skipped. Invalid UTF-8 characters will not result in a load failure. Error on column count mismatch allows fields to be added on either the source system side or the receiving side. If the source system adds new fields to the end of the data files, they'll be ignored by the pipe copy into. If new fields are added to the end of the pipe copy into command before they're added to the source system feed, they'll be output as null values. This means that schema changes don't have to be tightly coupled between the source system and the Snowflake pipe. Now the pipe. Note that it references the notification integration object. Its purpose is to automatically initiate a copy into command whenever new files arrive in the cloud storage folder referenced by the stage object. The map update pipe contains a copy into command which loads data files in the cloud storage location referenced by the stage object into the tbmapupdate Snowflake table, using the load option specified in the CSV pipe no header file format object. Using the Snowflake object construct function, the input file delimited fields are loaded in sequence into a variant field named input raw, which will subsequently be referenced as a JSON array in the programming. In front of the input raw field are two metadata fields provided by Snowflake which identify the full input file path and the row sequence of each record within the input file. After the input raw are two fields which identify the system date and time the file was loaded and the user executing the pipe into, copy into. I've included but commented out the copy into force equals true option. By default, the copy command will not reload data from a set of staged data files which have not changed. The force equals true option allows us to manually reload files which have previously been loaded. This option is not allowed when the copy is run inside a pipe. Also included but commented out is a pattern option. The pattern option allows us to selectively load files in a stage location based on a pattern string. My intention was to use a single stage folder for all entities in this system and let the pattern sort them out. Unfortunately, the pattern doesn't seem to work inside a pipe, though it works fine when the copy command is run manually. I'm not sure why this is, but for the time being, I'm creating separate cloud source folders for each entity's data files. We'll be going over these pipe-related commands in the demo coming up next. This is the staging table, which is the target for the pipe. Note how the columns correspond to the pipe's copy command, with a single variant column for input raw, which contains all of the raw input file fields. I've also included the stream in this script, because any time a table which is referenced by a stream is recreated, the stream must also be recreated. For the SM map update stream, I'm explicitly indicating that I'm only concerned with inserts into the TB map update table. The map update view provides a consumer-friendly version of the map update table, which will subsequently be used by the stored procedure queries. In addition to the file path and row sequence provided by Snowflake copy metadata, it separately parses out the input file name. It also creates distinct columns for the input raw JSON values in the map update table. The record has two sections. In the first section, the raw input values are cached to their appropriate data types. The second half of the record contains the original raw input as unconverted string values. Comparing fields in the two sections lets us know when invalid data type values have been sent and what the original values were. Although this system dynamically generates many Snowflake compute tasks, TA map update start is the only persistent task not created in a stored procedure. Every minute, it checks for new data in the TB map update table, which is captured in stream SM map update. Because the task is only referencing metadata value system stream has data, It executes in Snowflake's Cloud Services layer and doesn't accrue compute credits. At the point where the stream has data, which means that the pipe has loaded data into the map update table, the map update start task will execute and invoke stored procedure SP map update start. We'll be reviewing the queries at the bottom of the script in the next section. Because I want to be aware of charges I'm accruing, I've created a resource monitor object to monitor compute credits in my warehouse. In this case, I set the quota to 100 credits, which for an extra small warehouse is $2 per credit would be $200. I've set percentages for notifications and set my warehouse to be suspended when I reach 100% of the quota. If any tasks are processing when I reach the quota, no new tasks will initiate, but the running tasks will be allowed to finish. I've set the monitor to immediately suspend any running tasks if credits get to 100% of the quota. Note how this is done under the context of the account admin role. I also have a script to grant execute rights on tasks and to create a specific task role for executing tasks. In a new Snowflake installation, the system default is US West Coast time. I've changed this to UTC. Again, this is done under the account admin role. Now, let's look at some of the other tables used by the system. tbmap is the target Snowflake table which will be updated from the map update data. tbJobList contains the list of jobs which must be run to process all of the updates. It's populated in stored procedure SP_entity_start, which we'll be reviewing in a later section. tbJobList has one entry for each entity, map update in our demo, a month of daily version dates, and a type of SQL update, delete, insert, or update. If a job must be run after another job due to job sequencing rules, the parent job ID is populated by stored procedure SP_set joblist dependencies, which we'll also be reviewing. The task ID contains the ID of the dynamically created Snowflake task which processes the job. Jobs are initially created with a status of to do, which progresses to pending, running, and finally completed or failed as the job is processed. tbTaskList has an entry for each Snowflake task which will be created to process a job. As with the joblist table, it's also populated inside stored procedure SP_entity_start, but by called subprocedure SP_set_tasklist, which we'll be looking at later. One task list entry is created for each distinct monthly version date in the map update table. These represent Snowflake tasks which can be run concurrently. Note the job ID field. While a task is running, this value will contain the ID of the job it's handling. This allows us to get all of the information for the current job from the job list table. Task status can either be ready, which means that the task queue is ready for work, or busy, which means that a task is executing in that queue. As you'll see later, the system's stored procedures call procedure SP write proclog to insert informational messages into a log table. The proclog table includes the name of the stored procedure which wrote the comment, the message text, and the system date time of the message. Note how a sequence object is used to provide an incrementing row number for entries into the table. The app config table contains key and value pairs. This is a repository of system values for informational purposes and for processing. An example is map update tasks max, which contains the maximum number of task queues which can be created for running jobs for the map update entity. The stored procedures also update values in the app config table, such as an entity's current update cycle start and end times. During processing, programming is in place to handle invalid input, for instance, invalid data-typed columns and duplicate candidate key records. These rejected records are logged in the reject summary table. Finally, the cycle history table, which contains historical start and end date times for each entity's update cycle. The system also has some utility views. The job task view combines the job list and task list tables as they're populated in the start process to provide a consolidated view of the jobs to be processed and the tasks processing them. We'll be using this in a demo section coming later. View task history is used to monitor recent task executions. The proc log is historical and very long. The logtail view is a simple convenience for viewing the most recent entries. Finally, the map update reject view lets us review the map update rejects for the most recent update cycle. There are also a couple of utility functions. The first one is used to look at the stage update data for the last cycle's rejects. Note how the select from the map update view dynamically uses Snowflake's time travel functionality to query the update table as it was at the time of the end of the most recent cycle. This is necessary because the update table is emptied at the end of the cycle, but is still accessible via time travel. There's also a function to view the complete map update table as it was at the end of the most recent update cycle. This function also uses time travel functionality. The only other Snowflake objects remaining to be seen in this system are the stored procedures, and we'll be going over those later. But before we end the section, I wanted to display some of the information available using the Snowflake show, describe, and get DDL queries. Extensive object state, descriptions, and creation scripts are available with these queries. We'll be using some of these in the upcoming demos. It's demo time. Let's watch a Snowflake pipe in action. We'll be using dBeaver to run queries to view the processing while it's in progress. Before we start, let's verify that the map update staging table and its stream are empty, as they would be after the previous update cycle. Because the work schema contains the persistent Snowflake objects, we'll set our context to it so that we don't have to qualify all of our objects. Now we'll verify that the staging table and the stream are empty. First, the table. And now the stream. Let's look at the pipe. Here's the copy command the pipe will execute. I'll copy it so we can take a look. You might remember this from the create pipe script we looked at earlier. Let's check the pipe status. The JSON output of this query gives us information on the current pipe status, including the execution state and the pending file count. These are the same two fields that SP entity start pulls. Here are the notification and storage integration objects used by the pipe and stage objects. And here's the stage object, which references the storage integration and is referenced as a source for the pipe's copy into command. This is the description of the file format object the copy into uses. We specified some of these attributes in the create script, the rest are defaults. And finally, here's the one persistent task, which is not dynamically created in the code. As we scroll the output to the right, see how the state equals started. And the command it will execute is the call to stored proc sp map update start, and the condition that will cause sp map update start to be called is stream sm map update having data, which would be because the pipe has copied files into table map update. As mentioned previously, the system stream has data attribute is evaluated in Snowflake's cloud services layer, and therefore the task execution has nominal or no cost to us. Okay, we're ready to start. Let's upload some data files to the cloud. We're going to use Microsoft Azure Storage Explorer to manually upload the sample files. In a real system, these files would obviously be copied from source system extracts. These are very small skeleton files, just to allow us to run a basic update cycle. In a later segment, we'll be creating much larger test files. The notification integration object will be letting the pipe know these have arrived, and the pipe will be copying them into the tbmap update table. We can query the information schema view in the table to view what's just been copied into the table. Here's what's now in the tbmap update table. And here's what's been loaded into the stream based on the updates to tbmap update. We are underway. In the processing flow, we've seen the PI map update pipe load the TB map update table from a cloud source location referenced by the ST map update stage object. As rows are inserted into TB map update, the changes are reflected in stream SM map update. When SM map update has data, its referencing task TA map update start executes, calling stored procedure SP map update start. Let's look at SP map update start in detail. SP map update start is a wrapper procedure for SP entity start, which gets called with the map update entity name parameter. SP entity start first checks the status of pipe PI map update. If there are files being processed or waiting to be processed, it exits, as the update cycle can't proceed until all pipe processing is completed. Task TA map update start will automatically execute again at its next scheduled time because stream SM map update still has data. If the pipe status shows that there are no files being processed or waiting to be processed, SP map update start begins the update cycle. The first thing it does is declare stream SM map update using a DML statement so that task TA map update start won't execute again during this update cycle. It next inserts the required job entries for this update cycle into the job list table. A record is inserted for each entity, version date, month end, update type, and file name. SP set job list dependencies is then called to update the job list parent job ID, which will be used to enforce job sequencing for jobs which cannot be run concurrently. SP set task list is then called to load the task list table with one entry per version date month up to the maximum limit defined in the app config table. These will represent the available task queues for the update cycle. When all of the cycle initialization processing is completed, SP entity start dynamically creates and activates task TA map update process, which we'll call SP map update process to begin the update processing. Each code walkthrough is preceded with a section that provides a context for the processing. You've just seen that section for the map update start procedure. In this code review, I'll be displaying the conventions I developed writing these procedures and some of the Snowflake functionality I've used. I'll also be mentioning gotchas I encountered along the way. I'm not a seasoned JavaScript or Snowflake programmer, and the creation of these procedures, and that for that matter the creation of this video, was a major learning experience for me. I'm hoping that my Snowflake programming and presentation skills will continue to improve as I go along, and I also hope you'll find some value in this. As this is going to end up being a very long video, I'm going to try to not repeat myself too much as we go from procedure to procedure, as many of the constructs are reused in all of the procedures. This first walkthrough will include many of the techniques I use in the subsequent procedures. Here's the SP map update start stored procedure. I've created all of the procedures under the sysadmin role. This procedure doesn't have any parameters, but most of the others do. I tend to use a varchar type for both input parameters and return values, and then cast the values as needed. By the way, Snowflake allows parameter overloading in procedures based on their signature. I didn't take advantage of this feature in this system. Unfortunately, JavaScript doesn't support function overloading, which would have been useful in the internal helper functions I'll be showing you shortly. Snowflake currently only supports the JavaScript language for stored procedures. As a 20-plus year SQL Server programmer, I was a bit horrified to realize there was no transact SQL equivalent in Snowflake procs. But as I've gone along, I've become increasingly comfortable with the environment. Still, modular development and debugging is sometimes a chore in this environment. A basic concept to keep in mind: in a Snowflake stored procedure, all Snowflake database access is via an API call, and the result, if required, must be obtained from a record set object. This is probably familiar territory for some, but as a SQL Server stored procedure programmer, it was new ground for me. You get used to it. All procedures are wrapped in a try block. The entity name is either passed as a parameter for generic procs or hard-coded for entity-specific procs. Every proc has a proc name variable which is used for logging. I couldn't locate an equivalent to SQL Server's object name proc ID, so it's hard-coded at the top of every proc. I eventually intend to have multiple schemas for separating programming from data, but other than the task queue schema, everything currently points to the same Snowflake work schema. The procedures are liberally sprinkled with log messages for monitoring what's going on with the running system. As there's a minor cost for any Snowflake query, I may eventually condition this on a debug variable, but for now I want to know everything. The logging process starts with populating a message variable and then calls an internal writeproc help function, passing it the message as a parameter. We'll talk about these in a minute. This procedure's purpose is to call generic proc sp entity start, passing it the map update entity name. Internal helper function callproc is used for this. When control is eventually returned to sp map update start from sp entity start, it will return a -1 for success or a 0 for failure. Let's talk a bit about the helper functions. Stored proc helper functions can be physically located before or after the main processing code. By my own convention, I always put them at the bottom. They're really useful for making code more concise and reducing bugs. There are two things I don't like about them. First, I find myself copying them repeatedly from proc to proc. This isn't really optimal, because if I change one, I'll have to copy that change everywhere. Hey Snowflake people, how about adding an enhancement to include these in a centralized object of some sort? I tried replacing the internal helper functions with external JavaScript functions, but it's really not the same thing. The other thing I don't like is that you can't overload the helper functions. That's apparently more of a JavaScript limitation than a Snowflake issue. Still, it would have been great to have overloading on the callproc helper functions, which take a various number of parameters. These helper functions are in all the procedures, so I'll go through them once here and then won't do it again for the other procedures unless there's a new function. If you're watching these code reviews out of sequence, oh well. function writeProclog is passed a message text parameter. As with all the helpers, it's wrapped in its own try-catch block. A SQL command variable is constructed to call stored procedure sp writeProclog. More on that in a minute. Positional placeholder variables are used in the command text. A SQL statement variable is created from the command, binding these positional placeholders to the global procedure name variable and the passed-in message. The statement is then executed. If there's an error, the catch block throws the error message text, globally replacing all new line characters with a space. The next helper function is callProc, which is obviously used to call a stored procedure. It's similar to writeProclog, but instead of binding the parameter, which is the name of the proc to be called, it just dynamically concatenates everything to construct the command. Note that I'm using backticks around all dynamically created SQL commands. I found this works best in that you don't have to escape single quotes, and the command string can be written on multiple lines for readability. You'll see that in some of the other procedures. When the statement is executed, a record set variable is returned. The next, or first row in the record set, is queried, and the first column in that record set, which is what the procedure returned, is returned to the helper function caller. The next helper function is getQuery. Its first parameter is the name of a column, which will be returned by the query passed in the second parameter. Here's a gotcha. The column name function must be passed an uppercase value. This is because internally in Snowflake, all object names are uppercase. Since this is a literal, if you try to reference it in non-uppercase, it just won't be found. So to be sure the value is passed in, but the column name is uppercase, the function uses the JavaScript toUppercase function. The function executes the passed-in query, then pulls the value associated with the passed-in column name. This value is passed back to the caller. There's a little nuance in the catch block. If the error is because nothing was returned, then we don't want to panic. The last helper function in this proc is execute command, which, as the name suggests, executes a passed-in Snowflake command and returns the results. Back up to the writeProclog function. As mentioned, it calls stored procedure sp writeProclog, passing in the name of the currently executing procedure in a log message. Here's that proc. As you can see, the sp writeProclog takes the proc name and the message parameters and inserts a row into the dBeaver table. Back to sp map update start. As we saw, its reason for being is to call sp entity start, passing in the map update entity name. Okay, take a deep breath. This one does a bit of work. We've already gone through the functionality in the preview. Here's the implementation. sp entity start takes the entity name as a parameter. Here's another gotcha. Stored procedure parameter names are internally uppercase and must be referenced as such. As you can see, when I populate the entity name variable with the value coming in via parm entity name, the parm entity name variable name is uppercased. Though not required, I also uppercase the value of the entity name to enforce consistency. Since this is a generic proc, all executing entities will share the same proc name. To avoid confusion in the proc log, I suffix the procedure name variable with the name of the entity that's being processed. Later on, we're going to be using a Snowflake function to sleep a few minutes between commands. I also define that value at the top. All of the procedures define a set of variables for contexts, constructed object names, and status codes. Here they are. There are some SQL commands I'll be executing down below that are defined here. Again, notice how they're enclosed in backticks, so I don't have to escape single quotes, and so I can separate the text into multiple lines for readability. The pipe status query is executing the pipe status command we saw previously using the pipe name constructed above. Since the result comes back as JSON, we're using the parse JSON Snowflake function to pull the execution state and pending file count from the output. These values are concatenated into a pipe-separated string. We also have command text variables to pause and resume the pipe. These will be used further on. Here we have a command to dynamically create an end of processing task and activate it. Typically, the end task will be created in SP entity process, but in the unlikely event that all piped-in data is invalid, we may want to end the update cycle here. The last query variable alters the end task status to resume. When a task is created, it's always assigned a suspended status. In order to activate it so it can execute on schedule, its status needs to be manually altered in this way. You'll see this again. As with all of the procs, a starting message is written to the log, and then we check the pipe status. This section is all about finding out if all of the input files have been loaded by the pipe and we can begin update processing. We first call the getQuery helper function, passing in an output column named out and passing in the pipe status query variable we created above. Because the result has been returned as a pipe-separated string, we use a split function to get the first value, which is the execution state, and the second value, which is the pending file count. We then do some checking on the execution state. Some of this is looking for unusual situations which will require us to suspend update processing. However, the most likely possibility is that either the pipe is still in the middle of processing or it's finished and we can start the update cycle. If the pending file count is greater than 0, the pipe is still processing files, and so we exit and wait for the next start task execution to try again. If the pipe is in running state, but all files have been processed, we want to stop the pipe as we don't want to load any more files into dBMapUpdate once we start update processing. We use function execute command to execute the pipe stop variable we declared above. We then execute an inline system wait query to sleep the number of seconds defined above. This is done to allow for some Snowflake latency stopping the pipe. Next, we check the pipe status again to see if it's paused. If it isn't, or if there are new files being processed, we exit and wait for the next task execution to try again. If the pipe is paused, we are ready to begin the update cycle. The first thing we do is use helper function setAppConfig to call storedproc sp setAppConfig to update the appconfig table with the start time of the latest map update cycle. sp setAppConfig receives key name and value parameters. Again, note at the bottom of the screen how the parameters must be referenced as uppercase. It then checks if the passed-in key name exists in table tbappconfig. If it does, it constructs and executes an update statement. If it doesn't, it executes an insert statement. When control is returned to SP entity start, we next insert a row into the TB cycle history table. This table has both the starting and ending date times for each entity's historical update cycles. At this point, we'll just create a new row with the start time and update the end time at the end of update processing. Remember that task TA_mapUpdateStart is still looking for data in stream SM_mapUpdate every minute, and we don't want to execute that task, which would call SP_mapUpdateStart again during this update cycle. To prevent this from happening, we create a dynamic DML statement referencing the stream as shown previously. This resets the stream pointer to 0 and prevents the map update start from executing. What follows are several queries to populate the job list table. The map update table might be very large, and we want to minimize the number of times we have to scan it, so we use temp tables to reduce the data to job list format. Note that for convenience, the queries reference the map update view instead of the actual table. Note the second temp table update query starting on line 227, where the sequencing requirement for update types is defined. Beginning on line 238, if any of the map update rows have required columns which failed typecasting or are missing, we mark them as rejects and update the reject summary table. Next, we summarize the data to a single record per file name, month, and update type. And finally, we insert the job information into the TB job list table. Note that we use the row number windowing function to generate a sequence number, and that all jobs start off in a to-do status. We next call SPSetJobList dependencies to populate the job list parent job ID for jobs which have a prerequisite job which must run before them. Let's take a look at that proc. This is another generic proc which takes in the name of the entity being processed. A variable representing a job list update query is constructed as a common table expression. The query uses Snowflake windowing functions to identify jobs with the same version date in multiple update types or file names. Parent jobs are identified based on deletes coming before inserts, coming before updates, and within this, older files being processed before newer files. We'll see the results of this query during the demo. The query is executed via execute command, and the results are returned to calling SPEntityStart. Following this, SPEntityStart calls proc SPSetTaskList to populate the task list table. Generic proc SPSetTaskList takes the entity name as a parameter. This proc is all about populating TB task list with a row for each task that can be executed in parallel for a given entity. The definition of this value is the lesser of the number of distinct months in the job list and the maximum number of task queues defined in the app config table. Some query strings are constructed which will be used in the processing. The task required query is first executed to determine the optimal number of tasks required based on the job list table. The appconfig max task query is then executed to check if there's a limit on the number of tasks which can execute concurrently for this entity. If it's less than what the job list asked for, we use it. We then make the inserts into the task list table. Note that the constructed query uses the Snowflake generator function. This is usually used to generate test data, and you'll see that I use it for this exact purpose later in this video. But here, we're using it to create a tally table for sequence of rows. Note that the tasks are initialized with a ready status. We execute the query and return the results to SPEntityStart. Back in SPEntityStart, though it's very unlikely, if all of the update data rows rejected due to invalid data in required fields, we will want to terminate the update cycle. We do this by dynamically creating and activating a TA mapUpdateEnd task, which will call a procedure to end processing. This would typically happen at the end of SPEntityProcess procedure, which we will be looking at next. Now, we're ready to begin processing the updates using the job list and task list tables. To do this, we create and activate a TA mapUpdateProcess task whose handler is stored procedure SP_map_update process. If you skipped ahead to this demo, I've covered all of the programming and prerequisite processing in prior segments. In our last demo, we piped in some map update input files from the cloud staging folder. This loaded the TB map update table, which was reflected in the stream SM map update. Task TA map update start is waiting for stream SM map update to have data. Once it does, TA map update calls stored proc SP map update start, the wrapper proc for SP entity start, which takes care of all of our update cycle initialization. If we run the same system stream has data query the task is conditioned on, it verifies that the stream now contains data, and the TA map update start task will now call SP map update start at its next execution time. Let's take a look at the proc log table to see what's happening. The proc log table entries show that SP map update start has called SP entity start, which is calling it subprocs, and is on its way through the map update cycle start processing. The pipe was in running state when we last checked. How is it now? There are no files being processed by the pipe, and it's been successfully paused. Now that SP entity start has paused the pipe, we don't want SP map update start to be called again by task TA map update start. When TA map update start executes, it's looking to see if stream SM map update has data. We clear the stream has data value by resetting stream SM map update's change pointer using a dummy DML query, reading from the stream and writing into a temp table. This results in the stream becoming empty. Let's see if that happened. The stream pointer has been reset, and it now has no data, so that TA map update start won't be triggered again during this update cycle. SP entity start and its subprocs populate the job list and task list tables. We went through the code previously. Now let's look at the data. First, the job list table. It's been populated with the distinct jobs which we'll need to run to process all of the updates in tbmap update. Each job has a sequential ID, and all jobs start with a status of to do. Notice how the version from date and version to date are full month periods, which will process all the daily data inside them. Also, the update codes and file names from the map update rows are specified. Let's look at a subset of the job list table columns to examine the job sequencing hierarchy. As we saw in the code review, the parent job ID is populated by subproc spsetJobList dependencies. This is used to enforce process sequencing. We can and will run updates for different months in parallel, but within a month, deletes need to be processed ahead of inserts, and inserts ahead of updates. Within an update type, we want to process oldest files ahead of more current files. For example, job ID 7 is an update job for March 2021. Its parent, job ID 6, is an insert job for the same month, which must run before it. Its parent, job ID 5, is another insert job with an earlier file name, which must run before it. That job's parent, job ID 4, is a delete job, which must run before it. That job's parent, job ID 3, is also a delete for the same month but has an earlier file name and must be the first job to run in the sequence. The three jobs without parents can run immediately in parallel as they have no dependencies. Because SP entity process hasn't started running yet, no tasks have been assigned to jobs, so the task ID field is unpopulated. Now the task list table. Before we go there, observe the distinct number of months in the job list table. There are 3: January, March, and April. The task list table has 3 rows, corresponding to the 3 months in the job list table, which can be processed in parallel. All of the task queues are ready to be assigned jobs to process. Because the job processing has not commenced, no jobs have been assigned and the job ID field is unpopulated. As mentioned in the Start Processing Code review, when deciding how many task queues to create in the task list table, the task's max key in the app config table is queried. If it is less than the number of distinct months in the job list table, then the value in app config will be used. Also note how the current cycle start time has been updated in app config. The start processing has also created a row in the cycle history table. Only the start time has been populated. The end time will be filled in during the cycle end processing. Remember that the last thing that SP_Entity_Start does is to dynamically create and activate a task named TA_map_update_process, which, when it executes, will call a procedure SP_Entity_process, passing the map update entity name as a parameter. Let's see if that's happened. And there it is. In addition to the original persistent start task, there's now a new dynamically created process task. The process task will now execute and call SP_map_update_process to take care of updating processing defined in the job list table. But we'll save that for an upcoming demo. Let's take a quick look through the entire proc log created during the start processing. One more thing before we finish this demo. You may remember from the code review that the start processing parses the tb_map_update input raw JSON looking for invalid version dates and update codes. It copies these to the reject summary table and bypasses them when populating the job list. In this run, we had 2 invalid version dates and also an invalid update code. Now, on to the processing component. As we just saw, at the end of procedure SP_Entity_Start, Snowflake task TA_map_update_process is dynamically created and activated. Its handler procedure is SP_map_update_process. SP_map_update_process is a wrapper proc which calls SP_Entity_process, passing the map update entity name as a parameter. SP_Entity_process uses the information in the job list and task list tables to dynamically create Snowflake tasks to run delete, insert, and update jobs. It also uses some sub-procedures to help with its processing. We'll go over these in detail in the upcoming code review section. For recursion control, SP_Entity_process first pauses task TA_Entity_process so that the task won't execute while SP_Entity_process is running. If all jobs haven't completed, SP_Entity_process starts looping through tb_jobless looking for jobs which are in to-do status. If it finds a to-do job, which means it isn't processing, job status equal running, or waiting to process, job status equal pending, it checks if the job has a parent job. If it does, and the parent job hasn't completed, the job is skipped for the time being. If the job can be processed, it next checks if there's a task queue in the task list which is ready to process a job. Task status equals ready. If there's a job which can be processed and a task queue ready to process it, the job is marked as pending. The task queue is marked as busy, and a dynamic task is created which invokes procedure SP_Entity_Task with the task's ID as its parameter. The processing will continue to spawn as many processing tasks as it can until there are no jobs which can be processed, no task queues available to run jobs, or all jobs have been processed. SP_Entity_Task calls the appropriate procedure to process the job's deletes, inserts, or updates. If there are still jobs to be processed, but none can currently be run, or there are no task queues which aren't busy, SPEntityProcess reactivates task TAEntityProcess and then exits. TAEntityProcess again executes at the next scheduled time and invokes SPEntityProcess. Once all jobs are completed, SPEntityProcess dynamically creates and activates task TA_mapUpdateN, whose handler is SPEntityN with the entity name as a parameter. SPEntityN takes care of all the end-of-update processing, including restarting the pipe to allow more update files to be loaded. Now that we've taken a look at an overview of the update processing in the last section, let's walk through the code. There's a lot to cover here, so take a deep breath and we'll get through it together. As we saw, SPEntityStart dynamically creates task TA_mapUpdateProcess, whose handler is SP_mapUpdateProcess. SP_mapUpdateProcess is a wrapper prop, which calls SPEntityProcess using helper function callproc, passing in the entity name to be processed, mapUpdate in this case. SPEntityProcess performs all of the processing tasks described in the last section, with the help of some call procedures we'll be looking at here. SPEntityProcess starts off by setting some query variables it will be executing later on. First is the number of jobs which need to run but haven't yet completed. Second is the SQL to dynamically generate task TA_mapUpdateEnd, which will be created when all jobs have completed. And last is a query to activate the end task. The first thing that happens is for invoking task TA_mapUpdateProcess to be suspended so that it won't execute while SPEntityProcess is running for mapUpdate. We then run the pending job count query we created above, which puts its result into a column named pending jobs. We set the more jobs variable to true or false based on whether there are more jobs left to process. If there are more jobs left to process, we enter the primary processing loop. Within the while loop, we call subproc SPGetNextJob, passing it entity name mapUpdate. SPGetNextJob gets the job ID of the next job that's ready to be processed. Let's take a look at it. SPGetNextJob takes the entity name as a parameter and returns the job ID of the next job to be run. If there are no jobs ready to be run, it returns a value of -1. To do this, it runs the query variable created at line 48. This query looks for jobs in to-do status, which don't have a parent job which hasn't completed. Back to the calling proc SPEntityProcess, at line 112, the value returned from SPGetNextJob is put into the next job ID variable. If a valid job ID was returned, SPEntityProcess next calls SPStartJobTask to take care of task processing. Note that the helper function callproc2 is used instead of function callproc because there are two parameters to be passed to SPStartJobTask. Here's helper function callproc2. Again, it might be nice to have function overloading available here, but that's not a big issue. Callproc SPStartJobTask orchestrates the task processing which handles the job's updates. The parameters passed to it are the entity name, mapUpdate in this case, and the ID of the job it will need to process. First, it constructs and executes a query to obtain the next available or ready status task ID. If all task queues are busy, it returns a value of -1 to SP entity process. Otherwise, the task ID it obtained will be used to process the job whose ID was passed in. Next, a query is constructed and executed to update the task list row associated with the task ID being used with the ID of the job list entry the task will be handling. Because the job list and task list are tightly coupled, a query is also constructed and executed to update the job list row being handled with the ID of the task taking care of it. Now that the job and the task are linked together, a Snowflake task named after the entity name, map update in this case, plus task ID, is dynamically created and activated to process the update task. The task has a handler of SP entity task with the entity name, map update in this case, and the task ID as parameters. Finally, the Snowflake task just created is altered to mark it as resumed for execution, and the ID of the task is passed back to the caller, SP entity process. Before we go back to SP entity process, let's take a look at SP entity task, the handler for map update task ID task just created. SP entity task takes parameters for the entity name and the task ID it's processing. The first thing it does is reconstruct the name of the task which called it. It then creates and executes a command to suspend that task. After suspending the task, it creates and executes a command to drop the calling task. Note that a Snowflake task must be suspended before it can be dropped. Next, it needs to get all of the job details, so it runs a query to get the job ID from the task list table, and then another query to pull the entity name, version from date, version to date, update code, and file name from the job list table. Note how, after executing the job list query command, it pulls the returned record set column values using the positional getColumnValue method. At this point, the job list entry for the job being processed is updated from status pending to status running. Then, the delete, insert, or update proc is constructed based on the value of the update code in the job list table. Note how the JavaScript switch statement is used to populate the called proc variable, which contains the name of the update procedure this job will use. The required delete, insert, or update proc is then called. We'll take a look at those in a minute. Based on the result of the called proc, the job list status is updated to completed or failed. Finally, the task list table is updated to reset the task queue entry to ready status so it can process another job. Control is then passed back to the caller, SP entity process. Now for the delete, insert, and update procs called from SP entity task. First, SP map update delete. It takes parameters for the range of version from and to dates to be processed, plus the file name field in the map update table. It then constructs and executes a command which populates a temp table with delete data from the map update view. Then it deletes from the target map table using the temp table. Note that if a specific record keys are referenced in the update data, it will delete just those rows. Otherwise, it will delete all rows matching the version dates in the update table. Now the insert proc, SP map update insert. This proc takes the same parameters as the delete proc. Again, a temp table is created from the update view to process the inserts. With the inserts, we'll be deleting then inserting based on the incoming update data, and duplicate key records in the same input file can create processing issues. To prevent this, a command is executed to capture the duplicates in a temp table. The query is constructed to keep the most current or last record in each set and mark the rest as duplicates. If there are duplicates, we add them to the reject summary table and then remove them from the temp table we'll be using to process the inserts. Next, we delete all rows from the target table, matching the rows we'll be inserting, and then we insert the update rows into the target table. Finally, the handler proc for updates, SPMapUpdate. Similar to the delete and insert procs, SPMapUpdate starts by populating variables used in its processing. Again, a temp table is created to process the updates. Then the updates are applied to the target table. In the update processing, if the raw JSON string value for a field, regardless of target data type, is equal to the word null, we null out the existing value. Otherwise, if the incoming value is not null, we replace it. If the incoming value is an empty string, we keep the original value. I've implemented the update logic this way for two reasons. One, I don't want to null out a target table value based on an input value which has been nulled out due to an invalid data type. Also, I'm allowing for update files where only columns to be updated have values in the input. That's it for the update processing. Let's go back to where we left off in SP Entity Process. We left SP Entity Process at line 114, calling SP Start Job Task with the entity name and the next job ID. As soon as Start Job Task started creating processing tasks, control was returned to SP Entity processing loop for more jobs to be processed. The loop keeps going until there are no more jobs to be processed, or no more jobs that can currently be processed, or no available task queues. If we exited the loop because there are no more jobs left to process, then we drop Snowflake task TA map update process, as we won't need it anymore. Remember that we previously suspended it, so we don't need to do that again here. Next, we create Snowflake task TA map update end, which has a handler of proc SP entity end with map update as a parameter, using the query variable at the top of the proc, and alter the task to set it to resume status for execution at the next scheduled time. The proc exits and processing will continue when TA map update end executes. If there are still jobs to be processed but none that can start now, we alter TA map update process to set it back to resume at the next scheduled execution and then exit. SP map update process will be called when the task next executes, and all of this will begin again. As a recap, we've uploaded these test data files to the cloud staging area, and they've been automatically piped into staging table dBMapUpdate. Recall that view MapUpdate provides a view of the staged data for the procs, with dBMapUpdate's input raw JSON value broken out into separate columns for the update procs to reference. Two sections exist in each row of the view, one with the columns transformed to their target data types, and one with the original raw character input values. Once the pipe has started loading data into dBMapUpdate, stream SMMapUpdate has data, which activates task TAMapUpdate start. TAMapUpdate start calls SPMapUpdate start to start the update cycle. The pipe is paused at the beginning of the start processing. and the job list and the task list tables, which drive the update processing, are populated. At this point in the processing, proc SP entity start has completed update cycle initialization and has created task TA map update process. When TA map update process executes, it calls SP map update process and update processing begins. For anyone who has skipped ahead to the demo, we went through this chart in detail in the Start Processing intro. Let's watch the update processing in action. There are two map update tasks at this point. TA map update start was created with a manual script and is persistent. It's not doing anything because the stream that triggers it, SM map update, has no data. TA map update process was just dynamically created at the end of SP entity start. It's going to call SP map update process at its next execution. We saw this view earlier. It displays the last 20 entries in the proc log. At this point, SP entity start has created TA map update process and then ended. We're waiting for the process task to execute and call SP map update process. And here it goes. As we saw in an earlier section, View Job Task combines the job list and the task list tables on job ID. This shows the tasks which have been assigned to update jobs. As tasks are assigned to jobs, this view will get filled out, showing the jobs transitioning from to do to pending to running and to completed. And that's it. Let's take a look at the proc log from the end of SP map update start. Notice that a minute elapses between the end of the start process until the process task it creates executes and calls SP map update process. And the target table, which has just been updated from map update. At this point, SP map update process has ended and all of the update processing is completed. SP entity process has dropped task TA map update process, which is no longer needed, and created task TA map update end. When this task executes, it will call SP_entity_n for entity name map update to end the update cycle. The last component is the end of processing procedure. As we saw in the last segment, when all update jobs have completed, SP_entity_process dynamically creates Snowflake task TA map update end, whose handler is SP_entity_end with a passed parameter value of the entity name, which is map update. When task TA map update end executes, its job is to close out the update cycle so that the system is ready to load new source data files. The first thing SP_entity_end does is use the Snowflake remove command to delete all input data files which have been successfully processed from the cloud folder referenced in the Snowflake stage object. Next, the TV map update staging table is cleared out in preparation for a new load cycle. Then we use the Snowflake clone command to create a zero-copy clone of the updated map target table. This is a point-in-time snapshot which provides a version of the table that won't be affected by in-process updates for query access by consumers. Last, we restart the Snowflake pipe so that new source input data files can be ingested. Now let's take a look at the programming. As with all of the top-level generic procedures, stored proc SP_entity_end's input parameter is the entity name to process map update. It initializes its variables, including 3 queries, which will suspend, then drop the calling TA map update end task and resume the paused Snowflake pipe. After a reasonableness check that all jobs for the entity have in fact completed, it extracts the current cycle start time for the entity from the app config table and then updates the cycle end time in the app config and cycle history tables. Next, it queries the jobless table to get a list of all input files for the entity which have been successfully processed and loops through this list, executing the Snowflake remove command for each file to delete it from the source cloud folder referenced in the Snowflake stage object we looked at previously. Again, note how the stage object is prefixed with an @ symbol. Once this is completed, the map update staging table is cleared out in preparation for loading new input files. Now we create a clone of the updated target table. By convention, snapshot tables have the same name as the original table with an S suffix. Finally, the alter pipe command, which was defined at the top of the program, is executed to resume the Snowflake pipe so that new files can be loaded into the map update table. Congratulations! You've made it to the end of the end. Now let's watch a demo of the end processing. Time for a demo of the end of cycle processing. To recap, before ending, SP_entity_process dynamically created task TA map update end. The handler for this task is SP_entity_end with the entity name map update as its input parameter. SP_entity_end will list and then remove all of the source input data files which have been successfully processed, then clear out the TB map update staging table so that it's empty when the pipe is restarted. A clone of the target table will be created for query access so that consumers aren't affected by in-process updates when the next update cycle begins. Finally, the pipe will be restarted. Let's watch. At this point, SP_entity_process has created task TA_entity_end before passing control back to SP map update process and ending. Task TA map update end will execute, calling SP_entity_end and performing the steps we've just discussed. We'll monitor with the proc log. That's it. All done. Let's check what it did. All tasks have been dropped, except the start task, which is waiting for new input data to arrive. Most of the source input files have been removed. All that's left are the two files which had invalid version date data that we saw in the start processing demo. There's now a cloned snapshot copy of the TB map table with an S suffix in the name. The update staging table has been emptied out, but we can still get at it. This Snowflake utility function we looked at previously can be used to generate a time travel query to view the map update table as it was at the beginning of the most recent update cycle. We copy the results of the function into the query window and execute it. Notice that we're referencing the view, but we could also directly query the underlying table. Try doing that with another database system. Finally, the pipe has been restarted so that more source files can be loaded and processed in the next update cycle. Hey, before we go, let's have a little fun and do something really stupid. Uh-oh! The clone's still there, but the original table is gone. What to do? Snowflake to the rescue! It's back. That's so cool. And with that, we've seen the entire update cycle. Of course, we were using extremely small files for the demo. What we need to do now is generate a large volume of test data to assess the scalability of this system. You've just finished a deep dive into the entire process summarized in this overview we saw at the beginning of the presentation. All that's left to talk about are some of the utility procedures that have been created to help with system development, testing, and management. Before we wrap up, let's take a very quick look at some of the utility procedures which have been created for this system. In an earlier segment, I briefly mentioned the concept of a Snowflake stream object becoming stale. What does this mean exactly? When a Snowflake stream is created, it begins tracking changes to an underlying Snowflake table. If the offset for the stream data is beyond the data retention period for that table, which means that we have unconsumed pending changes in the stream which precede the associated table's available history, the stream will become stale and unusable until it's recreated. The show streams command returns information on Snowflake streams. One of the columns at the end of the output is the date the stream will become stale. What does this mean to us? The system we're reviewing could potentially have many entities to maintain. Some of these entities may be infrequently changed. It's possible that the retention date for the update table for an entity might be exceeded without any updates being loaded. This would result in the associated stream which triggers the entity's start task from being unusable without manual intervention. The easiest way to reset a stream is to reference it in any kind of DML statement. SP prevent stale streams is meant to be scheduled to run once a day under a task. It takes in a parameter which indicates the number of days before the stale after date in show streams to take action. After validating the incoming parameter, it invokes the show streams command to get a list of all streams with their stale after date. It then parses the result of that query and for each row, which is within the number of days in the parameter of becoming stale, extracts the stream name and the number of days from the current date until the stream will become stale, using the result scan last query ID function. Note: Snowflake logs the history of all executed queries. This is an example of extracting and parsing the most recent query result in the current session. The program then uses the statement's getRowCount method to identify the number of rows returned in the command we just executed. This will be the number of rows we need to loop through in our processing. A temp table is created as a dummy repository for DML statements we'll be executing to reset the stream pointers, and we begin looping through the showStreams result. In the while loop, for each stream which we need to reset, we execute a dummy DML command inserting into the temp table and referencing the stream. At the end of the loop, we drop the temp table. As mentioned before, this isn't strictly necessary as temp tables are automatically dropped when they go out of scope at the end of a procedure. The next utility program is SP suspend all tasks. We wouldn't really expect to need this in a running system, but during development and testing, we might possibly have many update tasks which have been dynamically created in the queue schema, which we want to suspend to prevent further executions. This proc takes in the entity name to be processed. The purpose of this proc is to put all tasks for the specified entity into suspended status. The tasks will still exist, but they won't execute. There are two loops, a while loop inside a for loop. We are dynamically creating top-level tasks in a control schema and also update tasks in a queue schema. The for loop allows us to sequentially process both of these schemas. Inside the for loop, we first execute the showTasks command for the passed-in entity and the schema specified in the for loop. The number of rows returned from that query is the number of tasks we'll be processing in the while loop. Inside the embedded while loop, we execute a command to cancel in-process executions, and then another command to alter the task to change its status to suspended. A point of clarification here. When a Snowflake task is suspended or dropped, in-process executions will continue to run until they complete. The cancel ongoing executions query does exactly what the name implies. A separate proc also exists which only cancels in-process task executions. As you might imagine, it's very similar to the procedure we just looked at. In some cases, suspending or canceling tasks isn't sufficient, and we might need to also drop all task objects. SP drop all tasks is used for that purpose. It's similar to what we've just seen. However, in this case, SP suspend all tasks is called first in line 68. This is because a Snowflake task must be suspended before it can be dropped. Then similar processing takes place, except in this case a drop task command is executed. Notice that we do not drop the entity's start task. This is a persistent task which is not dynamically created with code. To just suspend an entity's start task, we used SP suspend start task. And to resume an entity's start task after it's been suspended, we use SP resume start task. Note the alter task command on line 44. In some cases, we may want to reset an entity's start stream to prevent the associated start task from executing. SP clear start stream is used for this. As we've seen previously, a temp table is created for the result of a dummy DML statement, which is then executed to reset the change pointer on the start stream. If we want to manually pause an entity's pipe, we use SP pause pipe. In the same way we saw in the start processing, this proc constructs the pipe name and creates query variables to set the pipe to paused and to query the pipe status to verify that it has been paused. There's also a variable for the number of seconds to wait to check the pipe after trying to pause it. Then the pause, wait, and status queries are executed, and the results are verified. A similar proc is used to manually resume a paused pipe. When developing this system, I sometimes wanted to reset file ingestion for the map update entity. SPPause map update was created for this purpose. It calls a sequence of procs to pause the pipe, suspend the start task, and clear the stream updated by the pipe. On the flip side, SPResume map update resumes map update pipe processing after it's been paused. It calls SPResume pipe and SPResume start task. After developing and testing a system, we want to get some idea how it will scale. In order to do this, sufficient test data needs to be generated. SPGen test files map update was created for this purpose. The procedure takes 4 parameters. First is a D or I value, which indicates whether we want to create, delete, or insert data. In the initial version, I'm not volume testing updates, which I anticipate to be ad hoc and low volume. The second parameter is the number of months I want to create data for. The third is the number of test rows I want to create for each month. And finally, whether or not to create compressed gzip data files. Lines 33 and 34 have some examples of calling the proc. After setting some defaults and validating the parameters, we extract the current system date in line 128 to use in our file names, and then set a query variable to create a temporary file format object to use in our file exports. This file format is similar to the permanent CSV pipe no header format we use to pipe in data files, but it has a compression option which is conditioned on the associated procedure parameter. Next, we calculate some values that tell us how many days of data we need to create and how many months back our data will go from the current date. We're now ready to generate the data files. If we're creating delete file, we first create and populate a temp table with the generated delete data. Note that we're using the Snowflake generator function for this. Then we create and execute a query to run a copy into command. This is similar to the copy into command in the pipe we looked at earlier, but in that case we were copying from a file into a table. In this case, we're copying from the temp table we just populated into a file in the cloud staging folder using the file format we just created. If we're creating insert data, we populate another temp table using a Snowflake common table expression, which again uses the generator function to create a virtual tally table, and then selects all of the map update columns, and outer joins to another generator table which supplies string and numeric random values. For inserts, we're going to want to create one file for each month of test rows. So if we ask for 12 months of data with 1,000 rows per month, we'll be creating 12 files with 1,000 records in each file. We create a temp table for this purpose and execute a query to get the count of months, which will be the file count. As a convenience, so we can use the select star when we create the file extracts, we alter the temp table to remove the leading month-end column, which is not part of the map update record format. Now, we loop through the months, executing a copy into for each month to export the month of data into a separate data file in the cloud staging area. Again, using the file format we created above. For the last demo, let's generate some representative test data using the SPGen test files map update stored procedure we just reviewed. I'm going to grab a sample call for creating insert files from the comments at the top of the proc and paste it into my query window. As you recall, the last parameter used by the dynamically created file format object to determine whether the output files from the copy command will be compressed or not. False means the proc will generate uncompressed text files. We probably want the files to be gzip format, so I'll change that to true. Then I'll execute the proc. Not very exciting. It returned a -1, meaning it ran successfully. Let's see what we generated up in the cloud staging area. And there they are. The pipe is now processing these. There are now 376,000 rows in the TP map update table. Here's some of the content. Let's look at the view. Now we have some nice data to work with. Some potential enhancements are under consideration for this system. You may have noticed that inside the update procedures, we're not using explicit transactions to commit or roll back groups of DML statements. In a rerunnable process such as this, explicit transactions may be unnecessary and could introduce additional processing overhead. I'm not sure, but I'm curious to try it and examine the results, bearing in mind that Snowflake transaction isolation is currently more limited than with other database management systems. The insert, delete, update procs for the map update table are specific to the structure of the source map update and target map table. There's no reason why these couldn't reference system metadata and become generic like the other procs, to be used for all entities. As the objective is to replicate source data to Snowflake target tables, it seems advisable to have some sort of process to verify the source and target row counts agree. I've tried various techniques for creating dynamic time travel queries. None have been entirely satisfactory. One limitation of Snowflake is that stored procedures can't return multiple row result sets. One workaround is to return JSON, which can have multiple nested rows, but that's not terribly consumer-friendly. Snowflake SQL functions are fairly limited, but Snowflake supports JavaScript for table functions, and this might be a good choice for replacing some of the static scripted queries with parameterized functions. Finally, the output of this system is ultimately meant to be shared among multiple consumers. Implementing a secure data sharing environment is a key benefit to publishing to Snowflake. Thanks very much for watching. I hope you found some of this useful. And good luck with your Snowflake adventures.